Okay. You could see that, right?
Yeah,
Okay. All right. So yeah, thanks a lot for the invitation. And I've known Nima for a long time, and this morning uh discussion about in-memory computing is definitely a very good platform. Thanks for building this great platform. Today, I'll probably take some time like to quickly introduce some recent works I've done in my lab. Um, uh, about efficient in-memory computing circuits and systems for AI with hardware and algorithm co-design. And most of this work are done by my PhD students, and some of them are already graduated, some of them are still here at ASU. And as we all know, right now, the deep learning is definitely very successful. There's has been widely used in many different regions, NLP, computer vision, and etc. But typically there are two ways when we actually accelerate AI. When we talk about hey computing of AI, we could actually deploy the AI into the cloud service. Of course, that's more powerful and it is very very widely used. But the other extreme is, we could deploy AI into the edge devices without, too much of this internet communication, but locally, this AI could compute it. It can be used in, this latency sensitive or, it will avoid this, communication congestion issues. So both are very, very popular. For the edge AI computing particularly, the issue is if we want to actually deploy the model into AI, there is issues from both the hardware side and also the algorithm side. From the algorithm side, the model is becoming larger and larger, of course, right? With the time going on, the model is become large and the computation is even become more complex with the most recent, this transformer-based mainstream. Or from the hardware side, the memory communication becomes pretty much the main, uh, bottleneck when we actually look at the computing profile of the whole computer system. The off-chip communication is actually taking more time than the computing on chip itself. So most of the time, the system is waiting for the off-chip data communication. So that's actually the memory wall issue we are talking about in the community for a long while. So that motivates, this in-memory computing domain. So we're trying to find a way if we can actually process the data within the memory to minimize the data communication between, logic and memory. So we have started working on this like almost like 10 years ago, and there's quite a amount of things going on. It's not just for AI, for many data intensive computations we have explored. This is actually a very high-level overview of my lab at ASU. We call it our Efficient, Secure, and Intelligent Computing Laboratory. So we are computer engineering, so we are working cross-layer. So my lab has work on, both algorithm and also the hardware. We are focusing to, improve the efficiency as well as the security and privacy of the AI computing system. So today I probably will take some time to only talk about the AI performance and efficiency, but we do have some work on the security and privacy as well, trying to investigate the security and privacy of the AI. So for example, for the first part, so our objective is, we're trying to explore different platform that can be leveraged for in-memory computing, either CMOS, either, emerging memory technology, such as magnetic RAM or resistive RAM, to build the computing components within this memory technology for AI, so that can be used in many different AI scenarios, wearable AI, smart IoT, smart health, and etc. So I probably will quickly go through several, recent AI hardware we have developed in our lab, and also a few algorithm co-design trying to make the system, more efficient based on our, hardware design. So let's first talk about the hardware. And this is actually a very high-level summary we have done in the past few years. The chip prototype we have developed based on, CMOS technology, particularly the SRAM technology. And on the right is mainly the non-volatile memories, mainly the uh, emerging technology based on resistive RAM and also magnetic RAM. So let's first check this CMOS chip we have developed recently. I picked, one of the example is it was present in recent this year CICC. We are using 28 nanometers SRAM technology, trying to build a sparse in-memory matrix convolution engine within the chip. So let's first look at this sparse convolution or sparse neural network. So prune it's mainly coming from the pruning of the network, right? The pruning of the network has been discussed for a very long time in the community because the model we developed for AI most of the time is redundant. There's a lot of zero, but this zero may actually distribute in a very different way. For example, when we actually prune out these zero values um, in the weight matrix, so sometimes it can be unstructured or structured. Structure means like those zero distribution has to be followed in a special pattern. For example, the entire filter is zero, so you can prune this filter. You don't need to compute this filter, or the entire channel even is zero, so you can prune entire channel. So that's actually more structured. Unstructured means like the zero could be anywhere. It's not following a specific pattern, even though it's a sparse, but there's no specific pattern. The most recent NVIDIA GPU, for example, beyond Ampere architecture, for example, A100 or even Hopper architecture, H100, for example, they are supporting a very specific structured sparse matrix processing, which is called N2M, structured sparsity processing. For example, the N2M means like every N element out of every consecutive M element they are zero. So for example, the 2 to 4 sparsity shown in this picture, the white dot is actually zero. The green dot is actually, non-zero. So basically, there are two white dots for every four consecutive, value you can see here. So the good thing about that is they could actually only store the non-zero value and also their corresponding index. They can just using 2-bit index to compress the weight. So you pretty much get almost a half of the size, and they could only process the elements of the non-zero within the GPU. So roughly they can get almost a 2x, peak performance improvement and some, certainly some, energy efficiency improvement. But there's no in-memory computing chips that can actually do that. So this is actually the chip prototype we have done this year, presently in CICC. First, I mean, this is in-memory computing macro. So the memory is SRAM. It's a parallel processing. So in general, the architecture has 16 column groups, and every group has 32 row groups. And all of those computations happen within these row groups. And within these row groups, we are storing the weight and index, following the similar pattern of the NVIDIA, but we support also other encoding mechanism I will talk about later. So um, we support actually two types of the sparse encoding method. One is a CSC, it's a compressed sparse column. The other is run length encoding. Of course, this N2M structured sparsity is we're using CSC, the compressor sparse column, to encode that, following the similar way as NVIDIA does. So all the in-memory computing happens within this single unit in this row group. So this row group was divided into two rows, the top row and the column row. And so the 10T cell is actually store the weight and also doing the computing. The 60 cell on the right is actually its corresponding index. It's reconfigurable. You can store, 4-bit weight in the top row and another 4-bit in the bottom row. Or if you're processing like integer 8, you can combine this row column and using all of the 8-bit 10T cell to store your integer 8 format. So how the in-memory computing was done in this SRAM, it was shown on the left here. So basically, it's depending on the traditional 60 SRAM transistor. So let's say assuming of the weight, one single bit W and WB was stored in this SRAM cell. And it's following a bit serial pattern. So basically your input activation, for example, IA0 and IA1, I mean, support pretty much to any bits. For example, if it's 4-bit or 8-bit, you can send like 2-bit at one cycle. Because the design here, we support like processing 2-bit input at one single cycle. So how it was done is, for example, if you look at T1 and T2, this is a two NMOS transistor. The gate was connected with the data storing place of the W and WB, so they are complementary. So for example, if the weight stored here is 1, so the transistor T2 will be turned on. Your input activation, if it's 0, then it will pass into DPO, which is your dot product output, will be 0. And if input activation is 1, then you will also send into 1. But if your weight is 0, so T2 will be turned off, and then no matter whatever value is your input activation is 0 or 1, the DPO output will be 0. So through that way, you can see that it's actually doing a bitwise AND operation. But if we're doing everything in digital and following a bit serial way, this bitwise AND operation is actually a single bit multiplication operation. But we actually have another transistor T3 and T4 on the bottom, so you can take care of the processing of another input activation 1. So in general, this cell is doing like 2-bit weight and 1-bit and 2-bit input and 1-bit weight partial product for a single cycle. So if you have an integer 4 format, you need 2 cycles to finish the dot product for one single bit. And if you have 8-bit, you probably need 4 cycles to do that. And of course, all of these 4 bits you can turn on them at the same time, so you can do this parallel processing to process a 4-bit weight at the same cycle as well, right? And then there's a partial the way we are doing the sparse encoding is your index was stored next to it and in the 60 transistor. So basically, you could actually, there's a comparator here, which is a encoder here. So it's trying to compare with your index, trying to see in current cycle, are we actually processing this index? If we are, which means, hey, this is a non-zero. So you need to set into the next level for accumulation. But if you're not processing the current value, which means this is actually 0, so it will not send into the next level for the accumulation. So you just, skip the accumulation of this value. So that way we can do this sparse processing. And of course, I mean, the whole computation is a pipeline design. You actually need 2 cycles to finish the completely MAC operation, because the first cycle is you need to do the multiplication, the bitwise multiplication and comparison, which is more like encoding, right? Sparse encoding. And then you need to send into the shift accumulator, which is shared across a whole column group around this across these 32 row groups. So you could actually accumulate the partial sum and send into the next level for the further, computation. So the encoding method we are following is this, CSC or rand length encoding. Just give you an example. For example, this is a sparse matrix on the top left. W00, W02, they are non-zero values, and all of the other values are 0, for example, here. So if you want to compress the weight, the way you do is you only store this non-zero value here. In the middle is a weight matrix, and corresponding the identity, the index matrix also has to be stored, associated with this weight. And then when you do the computing, because you are doing the convolution, so you are actually doing the multiplication and accumulation in the row wise. So you just transpose it and write into your SRAM, single column. The way we are doing that is because you can do the parallel processing by turning on all of those columns at the same time. So you can do the accumulation for every column at the same time. So that's a parallel processing to maximize the parallelism of the whole chip. That's actually a very important transpose mapping algorithm we are following. And the other one is rand length encoding. You can also, the chips also support that. The rand length means like it's not storing the absolute position of the weight, but they are actually storing the distance between 2 non-zero values. So in that way, the index range could be relatively smaller, but the chips support both. And this is actually the implementation in 28 nanometer TSMC technology. It's a single macro. It's a 64 by 128 SRAM array. And as you can tell, we tested the chip in the across different voltage from almost 0.6 to 1.2. And it can run at the maximum frequency of 1.16 gigahertz with around like 72 milliwatt. Um, we'll show you more results. So this is another indication of why we need to do sparse. So basically, if we do the sparse encoding, um, so we took, for example, the most popular ResNet 18 or some other, um, neural networks, convolutional neural network. And it's interesting, like most of those, convolutional neural network, because we are spotting this unstructured sparsity of the weight. So the sparsity can be actually high. Most of the time, we can easily get 80 to 90% of sparsity without losing any accuracy. This is a common setup for the community. But if it's a structure pruning, for example, filter-wise or channel-wise, you can only do probably, 40%, 50% maximum. So in general, you can actually save, quite an amount of area on chip because you are using much less number of, parameter to store your weight. The chip will actually directly process that sparse encoded weight. So we actually compared it with different most recent work published in, the circuit community. And it turns out I'll show you the data here. So this is actually comprehensive compression compared with, the other in-memory computing based on SRAM. It turns out our chips can get almost the highest performance in terms of the GOPS and almost among the top of the peak energy efficiency, represented in terms of the TOPS per watt, is Tagger operation per second per watt. And we define this figure of merit, combine the TOPS per watt, which is energy efficiency, multiplied by TOPS per millimeter square, which is the area efficiency, multiplied by, excuse me, multiplied by the number of weights you can store per kilobit. So compared with that, we're getting the best combined performance considering the energy efficiency, area efficiency, and also the number of weights you can store on chip, right? So that's actually the best that we could get, up to now. Um, why we do care about this convolutional neural network or this sparse processing, I can quickly show another example like why this is important. Because there's those sparse convolution is very, very important in many other applications, not just AI. For example, this wireless communication application, this neural BP decoder is a very important ultra fast speed wireless data decoder. It's basically, if you look at the algorithm, it's basically the sparse matrix multiplication. And luckily, our chip, inherently supports such kind of sparse matrix, multiplication. And in this particular wireless data communication, the sparsity can be sometimes as high as 99%. And if we are using our chip for this in-memory sparse processing directly, that can save, we actually compare with some most recent. So here, chip design for this wireless communication, and we can get almost 10 times of higher energy efficiency end to end in this wireless channel decoder. All right. So that's, some, very high level to give you idea like what kind of work we have done in the SRAM based in-memory computing. Next, I can show some results in the non-volatile memory, which is emerging memory technology. So let's first look at RAM. I mean, RAM is so popular. I think I don't need to talk too much how the RM works and how the crossbar is working. So in general, we most of the fabrication we are collaborating with different groups. For this particular work, we are collaborating with Professor Nate Katie from SUNY Polytech, which is actually IBM production line. So they could actually do those uh, monolithic integration of RM, particularly this RM is a hafnium dioxide. We could actually put, using it as a backend of line. So they can first fabricate your CMOS part and then, deposit the hafnium dioxide RM as one layer of the metal. So we can monolithic integrate the CMOS circuit and also with the resistive RAM together. So I mean, from the design point of view, um, we have earlier investigate, how to mitigate this non-ideal effect and how to mitigate, these noises of the device, I mean, etc. So that's what we did in the past few years. But most recently, we're working on this hybrid chip design, meaning we are actually leveraging this crossbar to do this analog computing, which is, ultra fast and also has a high power efficiency. But the issue is the it's an emerging technology, and this is analog computing. There's a lot of noise. So earlier we found, hey, the noise actually is so large and it's not friendly to to build a large scale system. So we are trying to build a hybrid system in recently. Hybrid system means like for every processing unit, we have a crossbar, for example, is doing this analog computing to get you the convolution output. But still, you have a small SRAM array and also a Mac engine associated with this crossbar. It's doing a digital-wise more accurate computing and trying to compensate certain kind of noise or certain kind of part of the computing, uh, to compensate certain kind of disadvantage of this analog computing. So let me show you some of the result we have. So why do we do that? And based on our test result, it looks like for this digital assisted analog, RM crossbar in-memory computing design, it can be more accurate and more efficient. It's a little bit counterintuitive, like you added extra hardware, you added extra, memory units. Why is actually more efficient? So let's first about the accurate. I mean, on the left is our measured distribution of the uh, you know, variation of the RM. As you can tell, the variation is very high. So earlier in 2019, we actually have a tool actually released. We call it PyTorch X. So which means we are developing an algorithm that trying to do those noise-aware training. It's called a noise injection adaptation. It's an end-to-end RM crossbar non-ideal effect adaptation for neural network mapping, which means we actually measure the um, variation distribution of your actual device, for example, RM, and then we build this stochastic noise model for the weight, and then this stochastic noise model will be actually added to the training phase. So during the training phase, the way your AI model could actually learn such kind of noise distribution, and the accuracy will be improved, much better. For example, earlier without without having this noise-aware training, the accuracy can be give you like 20% or 30% reduction if you directly do the mapping and measure the computation result from your chip. But right now, with this noise adaptation, we can get almost like, for example, 89% accuracy, which is very close to the full accuracy of, for example, 91, 92 for your ResNet 20 in Cepha 10 dataset. But that's one part of about this accuracy part. The other one is about the efficiency. So when we add this digital computing unit, the major benefits we can get is we found that you can relax the requirement of the ADC resolution. Because I mean that's very important to know that this is analog computing, but if we want to send the activation to the next layer for the further processing, it has to be converted into the digital domain for data communication. So ADC is pretty much a must in pretty much all those crossbar based analog computing. And if you do the whole chip measurement, you find that the ADC is almost like 80% or even higher of the power consumption of the overall system. So in that way, because we're using flash ADC, so the lower resolution of your ADC means the power consumption can be lower. So as I'm showing on in the plot on the right, the um, for example, the full precision is 3-bit ADC because this is only a partial sum. Of the 3-bit value will be sent into the next level for accumulation, so the accuracy might be higher. But for the partial sum, 3-bit ADC, let's say if it's a baseline, and what we found is if we can reduce that to 2-bit ADC or even 1-bit ADC, the power consumption can be significantly reduced by almost 1.9 times or 2.9 times if we can using lower bit ADC. But of course, if you're using lower bit ADC, the partial sound resolution will become low. That will affect your accuracy. That's what we're showing, in this table. If you're using 1-bit ADC and a 1-bit SRAM precision, the accuracy will be reduced only to 84. And if it's a 2-bit and a 1-bit ADC, the accuracy will become almost like 91. So that's actually a trade-off between the SRAM precision and also your ADC resolution. And in the end, what we found is, hey, if you can lower that with the SRAM module, with only like 1-bit SRAM Mac engine, you can get almost 91.15, which is very close to your baseline accuracy with even higher than 3-bit RAM, 3-bit ADC, which is almost 89%. So that's actually the more accurate and efficient computing I'm talking about by using this digital assisted analog in-memory computing. I mean, the paper will be released very soon. We have published our preliminary work in TCAT this year. We have more chips actually came out soon. I mean, please keep tuned. Um, for this particular round of tape out for hafnium dioxide with monolithic integration of the CMOS. Um, I mean, we have other works. It's not really to AI, but I can just take a few minutes, 1 or 2 minutes to talk about that. So for this RM, I mean, that's a very good candidate for non-volatile memory-based in-memory computing. It's not just using for AI. Recently, we have a GSSC paper just talk about, hey, those could be used for genome processing as well. We actually built the world first RM-based genome processing, which is for DNA alignment. Because, for example, if we want to know, your DNA information for every patient, right now, those are sequencing machine from every hospital. For example, they can take your blood and then get your DNA short reads. They cannot directly get your complete DNA information, but they only get the short read, which, this combination of the ATCG, but that's only like in the length of a few tens or at maximum hundreds. But our human genome length is 3 billion. So they need to align the location of this, short reads in the human reference genome. So this position information can tell the researcher a lot of information. But this whole process is very compute intensive, and actually 93% of time for the genome analysis is spent in the read alignment. This is actually the major bottleneck why right now not everyone can easily get your DNA analysis result, because you need to wait in the cloud service within the line to get those alignment to be done, and there's a lot of computation to be done. So we actually built this world first. I mean, I'll skip the detail. We actually built this world first genome alignment for short read alignment in memory. So leveraging this RM crossbar. In this case, because it's a genome, so we completely encode that into way is a digital. So we're using only a single bit of the RM, trying to minimize the effect of the noise, because this is genome processing. Rather than AI, they can tolerate certain noise, but genome processing, I mean, it needs to be precise. So we actually are leveraging the most state of our BWT result, BWT algorithm, which is more like deep learning in the AI community. Is the most state of art algorithm. So whenever we get every single RM array, it's a separate core. So once we get this short rate, they can be, partitioned into every single nucleotide and then processing every single core to parallel processing that. And they can very quickly get your position information. And I'll skip the details. It's not about AI. But here, we compared it with GPU, FPGA, and other CMOS ASIC design without this in-memory processing capability. Our monolithic integration of CMOS and RM chip, you can get almost like 10 times to 100 times faster speed and also higher energy efficiency compared with even this ASIC design, and of course compared with a GPU platform. It's not just 100 times, it's even a few thousand, a few tens of thousand higher energy efficiency compared with GPU. All right. So that's about some work about the RM. We are also, heavily working on magnetic random access memory, because I have done my PhD at Purdue, and we are mainly working on spintronics. So it's magnetic random access memory on the neuromorphic computing. Recently, we get a few project from NSF called Fuse. Fuse project is the future of a semiconductor. Future of semiconductor is part of the Chip Act in US. So we are collaborating with Stanford University and Duke University. We actually are developing a 3D structure of the uh, uh, SOTMRAM, which is called spin orbital torque magnetic random access memory. It was with liaison from Intel and Samsung. So the objective of this project is the traditional, commercialized MRAM, which is STT-MRAM, is a spin transfer torque magnetic random access memory. They typically, it's a two-terminal device, of course. They using one transistor, one MRAM, but the issue is the writing time is relatively longer and the writing current is higher. Even though, MRAM is commercialized, but its performance is, it's not, as high as we expected. So that actually limits its application in a lot of these high-speed cache or high-speed on-chip memory applications. So with the Stanford team, we are working together to develop a new SOTM RAM. Even though SOTM RAM has been there, but we are leveraging the geometry innovation of this SOTM RAM. So we can actually let the multiple MTG share a single, SOT line, and also leveraging both the ST and also SOT. SOT is a spin Hall effect, spin orbital torque effect. So that can actually reduce the uh, writing current and also improve the writing speed. So we are targeting for 1 nanosecond to 2 nanosecond switching time for those SOTM RAM, and also with less than tens of a microampere of writing current. And we have a working prototype now. It was not published. I mean, I cannot show now, but we'll publish that very soon, and we already reported to our liaison, the success of the prototype. And our team is trying to work together with Stanford and trying to build the in-memory computing components based on this new technology, and to be able to deploy the AI computing we talked about earlier. So the main idea is very similar with our SRAM design, but it's also following this completely digital way, because MRAM is not like RRAM. It's not multi-level, it's a single level digital memory. It has a relatively low on-off ratio, but if we're using it as a digital memory, that's not a big issue. So we can still leveraging the peripheral circuits I talked about earlier, using the sparse in-memory processing, etc., to process that. Based on our initial prototype, we this is our initial prototype. We have four MTGs shared a single SOT line. Um, this is not exactly the um, device we're using for this project, but this is a preliminary prototype we used, at Stanford team. And we're using this actually to benchmark our model, and we design the circuits and build the cross-layer simulator, trying to simulate the whole thing from the device side, from the circuit side, and also the architecture side. Our group actually developed a open source tool, EDA tool, trying to benchmark the SRAM and also the MRAM based in memory computing. It's open source in GitHub link. Feel free to download it and play with that. So you can actually benchmark cross-layer the performance of your circuit design to be applied into the AI application, etc. All right. Sorry, those are the a quick introduction about the hardware implementation of the in-memory computing my groups have done in the past, few years, in the SRAM side, in the resistor RAM side, and also in the magnetic RAM side. Hope, you get the basic idea how this thing, could be designed in the actual chip. Um, the next thing is I can probably take 5 minutes to talk about this algorithm co-design. So once we have the chip, as you can tell, they actually have very unique requirement. So if we cannot directly apply or deploy your AI algorithm into the hardware, I mean, you can, but you cannot fully leverage in the benefits, right? For example, those sparse processing, you certainly need to pre-process your model to make sure your model is as sparse as possible. Or, I mean, the data set we are supporting, for example, is integer 8. We're working on floating point number 8 chips right now. We're just sending it for tape audit, but it has been published. But as you can tell, the data format also has requirements. So that certainly requires certain kind of algorithm co-design. So in my lab, there's almost half of the students, they are working on the AI algorithm co-design, trying to make the model more efficient for inference and also more efficient for learning. So for the inference side, I mean, we are working on this model compression using, pruning, using quantization, using knowledge distillation, etc., and also trying to develop a dynamic, network, meaning in the runtime you can reconfigure the network, trying to run different size of your network in your hardware. So that's about, in the inference side. So in the efficient learning side, this is actually the main focus of our lab in the most recent years. We're trying to develop this on-chip learning. How can we leveraging the limited resources to do this edge-based on-chip learning, which are traditionally be considered as a very difficult job, because it's a very computing and a memory consuming process. But how can we do that? I can probably take 5 minutes to talk about this efficient learning side. I'll skip this inference side. I'll just talk about this learning side. Okay. So the background of this on-device learning is compared with this cloud-based computing, because cloud-based computing is pretty much when we trying to train the big AI model from scratch, from random initialization or whatever initialization you're using, and you have a lot of data to train to iteratively update your weight. So that's most of the time is done in the cloud. But when you deploy your model into Edge, right? And we have our own private data. You want your model to gradually learn your own private data, but you don't want to send your data to the cloud for the privacy issue. And also, um, you know, sometimes if everyone is sending a lot of data to the cloud may become congested. So in that case, this transfer learning or continual learning concept has been well investigated in the community, but we wanted to make it, learning on device, meaning you already have a pre-trained model and you have a small downstream task or a small downstream data set you want the model to learn. So how can we like quickly adapt? How can we quickly fine-tune those like small scale private data in your local device? That's actually our focus. Those training process is very compute and memory intensive. For example, this is experiments we have done. For example, if you're using this Edge GPU, NVIDIA, Jetson Nano, for example, it only costs you $200 and with only 4 GB of memory. So that's very small. And what we found is there's a lot of, continual learning algorithm. For example, this piggyback was trying to learn a mask because you don't want to learn every parameter. For example, you have 1 billion of parameters. I mean, for those continual learning, you certainly don't want to update every of your 1 billion parameters. You want to only update the necessary, parameters. It's of course a very important topic to select which parameters need to be programmed, but that's out of scope of the talk today. But as you can tell, there's a lot of pre-order work. For example, piggyback or parameter adapter. For example, LoRa, low rank adapter, is probably the most widely used continual learning adapter, which is learning a parallel network using low rank adapter, trying to learn the new weight rather than fine tune the entire model. But anyway, those are, very popular continual learning method. If we deploy that into the very powerful GPU, you barely can see any difference. For example, on the right here, in this red box, you can see it's almost no difference in the very powerful GPU. But if you actually deploy this continual learning algorithm in the very small GPU, at GPU, you can see a very different latency and the throughput or latency or throughput difference between different algorithms. Right? Sometimes it can be 3 times faster. Some algorithm can be 3 times worse. But why is that? I mean, we actually investigate that problem and we found that it's mainly because of the memory issue. So that's a memory what we are talking about, right? The topic of today. The memory issue means if we're directly fine-tune the weight, right? For example, in the backpropagation case, this is alpha I plus 1 is your activation of the next layer, alpha I is your previous layer, multiplied by the weight plus bias, right? This is the basics of your AI computing. And if you want to do the backpropagation, you need to get the derivation of the weight and also the derivation of the bias to be able to update the weight, right? To get the gradients. So if we get the gradients of the W, so the AI, which is your activation of your current layer, has to be multiplied by the gradients of your last layer. So meaning your on-chip memory has to cache this AI and also your last layer, activation as well. And this is actually very big. Most of the time, it will let the system wait for a very long time to waiting for the loading of this activation because you have a limited on-chip memory. So this is a modification application, as you can tell. But if this is a additive kind of relationship, the green arrow we are showing here. If this is additive, so when you get the derivation, you don't need to buffer the activation. You just need to calculate the, current layers activation to get the gradients. So you actually can save a lot of on-chip buffer, on-chip memory usage, and that will cause the significant time difference. That's what we found. If it's a multiplicative relationship, it actually causes a very large memory usage. But if it's an additive relationship, the no activation buffering is needed, so your system can be speed up. So based on that, we actually propose several different solutions, and this is one solution we proposed and published in 2022 CVPR. So we call it an additive attention adapter, DA3. So the way it does is we frozen the backbone. Remember that we have pre-trained backbone neural network. You don't need to train it. But when you actually learn your domain data, domain specific data, you just learn this adapter. And this adapter is in the additive relationship with your main branch. So when you calculate the gradients, this AI is completely, you can just disregard that because it's frozen and it's additive. You don't need to buffer that when you calculate the gradients of your adapter. So through that way, you can save significant amount of buffering of your on-chip memory. And this is a structure, we can skip that. But we compare with the most recent continual learning algorithm, we get the state-of-art accuracy, but as you can tell in the top bottom, the edge GPU implementation you have seen earlier, the orange one is our real implementation in the Jetson Nano compared with the other algorithm. You can tell that is the actual learning time is significantly reduced with the same learning accuracy, so the entire training time can be reduced almost by 3 times, right? Through this kind of idea and design. We have other solutions. We can skip that due to the time limit. Um, all right. Yeah. So this thing can also be used in the hybrid, uh, RM design we are talk about earlier. So besides the more accurate and efficient inference computation using our RM-based in-memory computing, so this adapter-based continual learning also brings a benefits for the on-chip learning used for this non-volatile memory. For example, this hybrid design I just talked about earlier. So when we actually using our adapter-based this continual learning, what we found is we can actually deploy the backbone model into your RM, but you can only using the SRAM part to map your adapter because your adapter is keep need to learn. So that will be mapped into the SRAM part. So through that way, we can do this on-chip continual learning or multitask learning, using non-volatile memory. But of course, you now keep programming the non-volatile memory, but using this hybrid design, so we can make the whole system learn your private data or your new data on chip, right? On chip. And of course, if you compare the yellow bar here is you completely rewrite all of the non-volatile memory, and the red bar here is trying to, only programming our SRAM part for the entire on-chip learning process. As you can tell, you're not rewrite every of the RAM and only rewrite the SRAM. So entirely the energy consumption can be significantly reduced, right? This is as expected. But the more important is the learning accuracy is almost the same when you're using these two kind of fine-tuning or this adapter-based continuous learning algorithm. Okay. All right. So I guess I will stop it here due to the time limit, and this already form a complete story about how we do let me quickly this is also summarize our work of how we can do this hardware design for in-memory computing. How do we develop the algorithm that can leverage in the unique property of this in-memory computing on different memory technology to build a more efficient AI system. And I thanks everyone for your attention, and I'm very happy to take any questions if you have.
Excellent. Thank you very much, Deliang. Let me also pause the record, stop the recording, and then we get to the question.